Okay, so for our next topic, I would like to address enzyme kinetics. So we've reviewed the contributions of enzymes to free energy changes into reactions, and now I want to look at the activity in the form of kinetics of enzymes. So what that essentially means is that we are going to measure an enzyme's activity by quantifying the amount of product formed. So remember our equation here. Ultimately, the enzyme is going to convert a substrate into a product. So we can measure this product formed over time. So because the enzymes are effective, we can measure a change in product over a change in time. Now, the product can be measured in different ways. Typically, the most common way is to use a spectrophotometer so that the product, for example, will absorb a certain wavelength that the substrate does not, so the appearance of product can be quantified by measuring absorption. So if we do this and we take, let's say, a fixed amount of enzyme and we add a certain quantity of substrate, what we will see in the beginning of the reaction is a linear relationship. And this makes sense because the more time you give the enzyme to work, it will convert over time the product formed. Eventually what will happen over time is this will level off, such that a certain time will be reached where no further product is formed. Now, what could be happening here? The major consideration that could be happening is that the substrate has been depleted. And of course, if there's no substrate, you will have no product formed. The other situation that could occur is that there could be what's called a feedback inhibition of product, so that more product form will feed back and inhibit the enzyme from catalyzing any more substrate to product. So this is done at a specific concentration of substrate. Now what if we maintain this concentration, the amount of enzyme in the reaction, and we add a little bit more substrate than we did in the first reaction? What will we see is an increased reaction rate. So the product will form faster. Makes sense. We have more substrate for the enzyme to work on, so the product will work faster. Ultimately, of course, we either run out of product, we run out of substrate, or we have feedback inhibition, and the amount of product formed levels off and does not increase. Now, what if, again, we do this one more time, but now we add even more substrate? Again, we'll have a linear relationship in the beginning because the enzyme will have plenty of substrate to work with, and it will catalyze the formation of product, which we can measure over time. And once again, we will see when we become depleted with substrate, the product formation falls off. Now, what can we do with this data? The important fact of this data is down in this region. Because if we're interested in the velocity kinetics of enzyme activity, we're interested in the speed, the rate of the enzyme's ability to convert substrate to product. Now, if we're out here in time, as the curve starts to level off, we are depleting the enzyme of substrate. So the enzyme doesn't have the full capacity to catalyze its reaction. It essentially becomes what's called substrate limiting. This portion of the reaction is not interesting because we cannot determine the maximal speed of the enzyme based on a limitation of its substrate. So what we're interested in primarily here is this region where we have maximal velocity at this particular substrate concentration. So what we're going to be interested in is the slope. And the slope, again, is change in product over change in time. And this will equal velocity of the reaction. Now notice we can calculate the slope for each one of the substrate concentrations that we did in these 3 separate experiments. Once we have this, and typically we use more than 3 substrate concentrations, typically we want to use at least 6 to 8 different substrate concentrations, we can determine velocity. We're going to call this VO for original velocity. The original velocity means the point where the enzyme has maximal amount of substrate, and that's when it's basically stepping on the gas immediately. And we are going to graph this versus substrate concentration. And if we do this, what we're going to see is a hyperbolic curve generated from these data up here to down here. Now the question is why isn't this linear? Well, that's because we have a rate limiting step. Now if we go back up to our expression here, if we calculate the reaction rates, K1, K minus 1 in the reverse direction, K2 and K minus 2 for product formation, we will see that this is essentially negligible. This will be the rate limiting step because conversion of substrate to product takes the longest time. It's the slowest rate. And so being the slowest rate, velocity will equal the rate K2 times the concentration of our transition state complex, ES. Because this is limiting, this equation here dictates a hyperbolic curve. Now, there's a couple of interesting parameters here on this curve that become very important. One is, notice that this VO at this level, no matter how much substrate we add, the rate velocity of the enzyme does not increase. So this is termed Vmax. The other important piece of information is this point, which is 1/2 Vmax. If we take 1/2 Vmax, draw it over to the line, drop a line down, we come up with a substrate concentration that defines Km. Now, what are these factors? Well, if we do an algebraic interpretation of this graph, we come up with a very familiar biochemical equation. This is called the Michaelis Menten equation. And simply, this equation defines this hyperbolic line. Now, why is this important? Well, what this determines is that the velocity of an enzyme is dependent on the substrate concentration. So if we write the equation this way, we see that if the substrate is very, very small, this is going to be the the velocity will be a fraction of Vmax, essentially down here. It will be dependent largely not on the substrate concentration, but on the Km. The Km equals the Michaelis constant, and this represents affinity, binding affinity of the substrate for the enzyme. So if we have a fraction of Vmax at small concentrations of substrate, it will be dependent on the Km, the affinity, so that the higher the affinity, the higher the original velocity. In contrast, if we have a very, very large amount of substrate, these numbers of substrate concentration become very large, dilutes out the effect of the Km, and that's only a small fraction of Vmax for the original velocity, and such that we essentially Vmax equals VO out in this region. So Vmax is an important determination of an enzyme's properties. The other important feature about 1/2 Vmax, deriving the Km, is that Km is affinity. So that means that an enzyme with a higher Km means a lower affinity. Now what does that mean? That seems a little counterintuitive. But the higher the Km means that it takes a higher substrate concentration to reach 1/2 Vmax. So if we contrast two enzymes, let's say we have two enzymes here we're comparing. This would be enzyme 1. This would be enzyme 2. Notice that the enzymes have equal Vmaxes. That implies that the enzymes have the same velocity of converting the substrate into product at high concentrations of substrate. But now let's look at 1/2 Vmax. Notice the Km for enzyme number 1 is much lower than the enzyme Km for enzyme number 2. So this implies that it takes more substrate to drive that 1/2 Vmax, which means it has a lower affinity. You need to have more substrate around to push that substrate into the active site of the enzyme. So higher Km equals lower affinity between the substrate and the enzyme. Conversely, if you have an enzyme with a lower Km, this means that this enzyme has a higher affinity, a higher binding affinity for the enzyme and substrate. So with Km and Vmax, we are able to derive quantitative values that permit us the opportunity to determine the characteristics of enzymes, and most importantly is to compare them, compare their activity.